Welcome back, Lecture 6. If you see some wet people in this classroom, it is absolutely pouring outside. And if you see some drops on me, some days I might slobber, but I haven't started slobbering yet. So this is rain, and if you look in the classroom, we've got some wet folks in here today. So thankfully it's raining because we need the rain desperately. We left off yesterday with kind of a standard equation for an ellipse. We did battle for about 15 minutes with the definition all the way to the equation in terms of x and y and a and b. And so we had for a standard form of an ellipse whose center was at the origin. This equation. And I think that's pretty much how we ended class. Is that correct?
Yeah.
So other than the center of this ellipse being at the origin, we don't really know at this point in time what A and B actually represent. Now we do know that we made a substitution in the process of getting to this equation. Does anybody remember that substitution that we made in terms of A and B and C? Say that again, please. A squared minus C squared equals B squared. We made that substitution. Let me kind of shuffle some terms around. That's what we did and made a substitution. This might be a little easier to remember as far as an ellipse is concerned, that the a squared value is the largest of the three, and it's the sum. A squared is the sum of the squares of the other two. Therefore, it has to be the largest of the three, if that's the case. So that might be the one you want to kind of recommit to memory if you originally had this memorized and you haven't done this for a while. Now, what are A and B? Well, we can kind of plot some points. If x is A or negative A and y is 0, don't those points work in this equation? If I plug in A for x and 0 for y, isn't that a legitimate equation? Right? This is 0 and this is 1. Or if I plug in negative A for x and 0 for y, again we get 1 equals 1. So those ought to be points on the ellipse. If that is true, give me two other points that you know are on this ellipse. 0b and 0 negative b. Thank you. Everybody see why they're points on this ellipse? And then originally, if you go back to the picture we started with, where were the foci? And then we'll just kind of use that, draw a little cleaner picture, do a couple of examples, and move on. What were the foci on my original diagram?
Negative C0 and C0.
Negative C0 and C0. So those are kind of the most important points to pick off of the equation when it's in this form. And you say, well, the foci aren't really given in this equation. That's true, but they're implicit in there in the fact that we know A and B, we can figure out C. So with this Pythagorean interrelationship of A, B, and C. So, since I don't have my other diagram handy, if I had an equation given to me in this form, I would come out here A units, to the left A units. Those would be the ends of the major axis, the larger, longer axis. The ends of the minor axis would be B units up on the y-axis and B units down on the y-axis. The foci would be somewhere in here. And the ellipse would be roughly in this position. Wasn't that a delightful trip to calculus class today? Yeah. So there's our ellipse, ends of the major axis, A units to the right, A units to the left, ends of the minor axis, B units up and B units down, and the foci then are actually on the major axis, shy of A because A is the largest value. So there's C units right and C units left. All right. Any issues or questions with that before we switch from letters to numbers? Is that okay? So not that much tougher, really. We just, instead of A squared, we have 16. Instead of B squared, we have 9. How do I mean, this is addition. So I could commute the order. I could have the y squared term first if I wanted to. And that's fine. You can. But how do you know where the major axis is?
A is the larger.
Jonathan. A is the larger. A squared is the larger denominator. Therefore, A is the larger of A and B, right? So even though if this is not listed first because it's a sum, it's the larger denominator, so that therefore A squared has got to be 16. A is 4. The smaller denominator is B squared, regardless of which order it appears. So B is 3. Jonathan?
So will A squared always be under X squared?
No. Okay, that's my next question, though. Thank you for that nice lead-in. So suppose that the larger denominator is underneath the y squared term. Tell me about that ellipse as it might be different from this one.
Major axis would be vertical.
Major axis would be vertical, either on or parallel to the y-axis. Is that okay?
Yeah.
So if the larger number is underneath the x squared term, that has its major axis either on or parallel to the x-axis. So it's indicative of the major axis. C here. How do we use the a squared and the b squared values to get the c squared or the c value? Okay? And the Pythagorean identity, a squared is the largest of the 3 distances involved in this ellipse. So it's from center to end of major axis. So it's got to be the largest of the 3. So a squared 16, b squared 9, so c squared has got to be nice clean value of
Triplet. Isn't it 3.5?
7. So c is the square root of 7. Okay, on the major axis. Yes,
Can't
question.
you just add A and B and then put a square root on it?
Add a and b.
Yeah.
Trip.
Because that's what we did. That's what you did. You just take the A value and B value, add it, and then put a square root over it. I just didn't know if that would be a shortcut.
Well, we didn't do that. We subtracted them. Right? If we added them, we'd get 25.
Subtracted them.
Right.
Yeah.
That's fine.
Yeah. Okay.
There you go. That'll work because that's exactly what we did. So c is the square root of 7. So if we were to sketch this, major axis in this case is on the x-axis. So 4 units out here and 4 units out here.
Yeah.
Those are sometimes called the vertices. Ends of the major axis is fine for the name. Minor axis, 0, 3. 0, negative 3. Foci, which I guess we can kind of go back to the definition as to what the foci happen to mean, but those are the 2 fixed points such that the sum of the distances from those 2 fixed points is a constant. That's what the foci are. So we'd come out here, square root of 7. Somebody give me an approximation for the square root of 7.
2.5.
2,
2 and 2 points something.
2.65, 2.7. Okay? Not that my diagram's going to be that good anyway. But there's one of the foci. Here's the other one. So they're on the major axis. I'm going to go ahead and sketch this thing. apologize that my diagrams aren't the greatest in the world, but that's a little closer. That's probably more like an ellipse than what I've been drawing to this point in time. Everybody okay with all those points that we located? This would be square root of 7, 0, negative square root of 7, 0. This point, which is not an end of a major axis or a minor axis, it's on the ellipse. So this distance plus this distance, the sum of the distances from those two original fixed points is a constant. Do we know what that is on this ellipse?
You can figure it out.
Okay, go all the way back to our first statement on where we figured out the equation, where we've got that distance plus the other distance equals something. You remember what that was?
Distance.
2a. So our equation started out distance plus distance equals 2a. So in every ellipse, the sum of the distances from the two fixed points is going to be twice a. So in this problem, this distance right here plus this distance for this particular ellipse is fixed, and what is it?
8.
It's 8. So that plus that is 8. That plus that is 8. That distance plus that distance is 8 for any point on this ellipse. The sum of the distances from that point to the two fixed points is 8. How do you think this equation would differ? Actually, let me just put another one up here. Questions on this before it gets moved? So let's say we have this, and I'm going to put the larger denominator underneath the y squared term, but it's not going to be y squared. It's going to be y minus 1, the quantity squared. And it's not just going to be x squared, it's going to be x plus 3, the quantity squared.
There, on a horizontal shift.
Okay, we've got a shift or a translation involved. So what was the case on the prior problem is that we didn't have an h and a k. So h and k, in essence, were 0, 0. That was the center. Now the center is what point? Negative 3, 1. And after we locate the center, is everything else relatively the same?
Yeah.
Yes, everything comes from the center. A units up, A units down, right? B units right, B units left, and then C units up and down on the major axis. So this would be our A squared, the larger denominator. This would be our B squared. So C squared is
3.
16. Square root of 16.
4.
Squared.
okay, C is 4, C squared is 16, is that right?
Yeah.
So our relationship is A squared equals B squared plus C squared. So C squared has got to be 16 and C is 4. So if we were sketching this, and these are just sketches, there's nothing that elaborate where these would be considered a graph. But a sketch of this, let's locate the center. Is there, everything goes from there, so we would go, what, 5 units up? Is that right? So the major axis won't be on the y-axis, it'll be parallel to the y-axis. So there's the vertices or ends of the major axis. B squared is 9, so B is 3. So there's the ends of the minor axis. I've never heard of a name given to them, like end of a major axis is called a vertex. I don't think they have a special name. And then 4 units on the major axis, so there would be one of the foci, and there would be the other. So we have this set of points roughly in the plane that looks something like that. Question?
What exactly are the foci? What are
The foci, again, you can probably kind of rough in the ellipse without even mentioning or drawing the foci, but all the way back to the definition, the foci are really the 2 points that more or less generate all points on the ellipse. Is that we know for this point to be on the ellipse, that distance plus that distance has got to be fixed, and in this particular ellipse, what is that fixed distance? 10. So this point right here, this distance plus that distance is 10. Now, as far as drawing it, we can draw it without it, but that's kind of what is true about every point on the ellipse.
just for the distance?
Some of the distances from those 2 fixed points is constant. Anything else before we move on to the last one? The last well, let me do one thing quickly. If you have a question, I'll still give you a chance. So let's suppose that we've got x squared over 9 plus y squared over 9 equals 1. Is that an ellipse?
No, it's
No,
a circle.
Yeah, it's an ellipse.
Oh.
But it's also a circle, right? It is an ellipse because one of these could be a squared and one could be b squared. Now, if a squared and b squared happen to be the same, that means the major axis and the minor axis are the same. Well, it's elliptical, but if the axes are the same, it's circular. So what happens then to c? I guess it's worth mentioning for this fact.
C is 0.
C is 0.
So there's only one focal point.
Right. So the 2 foci are, in fact, coinciding with the center, right?
Yeah.
So the closer the foci get to one another, the more circular that ellipse becomes. And in fact, when the 2 foci are at the center, it's still an ellipse, but it's a special ellipse called a circle. Okay, hyperbola. So hyperbola is very similar in definition and consequently very similar in equation to that of an ellipse. So it's the set of points in a plane. The difference whose distances from 2 fixed points, again called the foci, is a constant. We're not going to do that 15-minute battle with the equation. We're going to set up a diagram, go to the first step, and then we're going to put a few dots in there and say this would be the resulting equation, because the battle is pretty much the same as what we've already done. So let's say that our 2 fixed points are out here at C0 and negative C0. So we want a set of points such that the difference of the distances from 2 fixed points is a constant. That set of points and again, this is a rough sketch, ends up being positioned somehow in this fashion in the plane. So in order for this point right here to be a point on the hyperbola, this distance minus this distance is fixed for that particular hyperbola. So if this is some point xy, we would take the difference of the distances and we would set it equal to a constant, which again we would pick 2a for that. So we'll do the first step, kind of mention what the Pythagorean substitution would be, and then we'll go to the last step without doing all the intermediate steps. From xy to negative c0, there's the difference, the distance between those 2 points, minus this other distance, and that is constant. And again, we'll set that constant equal to 2a. So here's where we kind of separated the radicals, squared both sides, simplified, isolated the radical again, squared both sides. We did all that stuff. So the process is very similar. Okay, so I'm just going to use some dots. That goes quite a bit quicker. And the end result of this would be that. So if you have any doubts about that and you want to develop that equation and you want me to check it to make sure you've done that correct, I'll be glad to do that, but I doubt that I'll have anybody coming to me that wants to develop the standard form of the equation. All right, so here is the equation. Now, one substitution that is made in here, I usually kind of refer to the diagram to spark my memory on the A, B, C interrelationship. Back on ellipses, I know the furthest point that I plot from the center is from the center to the end of a major axis, which is A. So that reminds me that a squared is the sum of the squares of the other two. This one, the furthest point that you plot, is from center to focus, and that's C. So C is the largest value here. So in deriving this, which we did not do, we would have made that substitution. That Pythagorean relationship would lead us to that. That C squared is the sum of A squared and B squared. Why? How do you remember that? C is the largest distance involved in the equation of a hyperbola because the furthest you go from the center to plot a point is from center to focus, and that's C units. Questions? I know I'm skipping a lot of steps, but we've already done battle with that, and I don't know that we're going to gain anything by doing that same battle again. If the x squared term is first, then that means we have a parabola, a hyperbola that has this is called the transverse axis. If you connect the two branches of the hyperbola, then that line segment that connects them is called the transverse, trans meaning across, so it goes across from one to the other. That's the transverse axis. So this means the transverse axis is either on the x-axis, like it is here, or if it's elsewhere, it's at least parallel to the x-axis. That's if the x squared term comes first. If the y squared term happens to come first, then the transverse axis is vertical as opposed to horizontal. Is a squared necessarily larger than b squared?
No.
There is no size interrelationship that is fixed because c squared is the sum of the other two squares. So a squared could be smaller than b squared. A squared will always be the denominator of the positive term. B squared will be the denominator of the negative term. So there are some subtle differences. Let's take, let's save a little bit of time and not do one with A's and B's and C's. Let's go ahead and say that this is x squared over 9 minus y squared over 16 equals 1. First of all, what's the key indicator that this is a hyperbola and not an ellipse?
The negative.
Okay, the subtraction. So and isn't that also true in how the definitions differ? One is the sum of the distances from two fixed points. There's a plus sign there. The other is the difference of the distances from two fixed points, so there's a different sign there. So very conveniently, the equations kind of mirror the subtle changes in definition. So a squared is going to be 9. B squared is going to be 16. C squared is going to be, remember, C is the largest value, so it's the sum of the squares of the other two. 25?
5.
So C is 5. Transverse axis on the x-axis or on the y-axis?
X-axis.
On the x-axis, because the x term is the positive term. Now let's bless you. Let's suppose that you forget that. Not that you've ever forgotten anything. Everything you've ever heard, you can regurgitate from the time you can remember. Drop this term out. How would you drop this term out as far as plotting a point? Wouldn't you say y is 0? That drops this term out. So if y is 0, what can x be such that this term minus 0 is 1? 3 or negative 3. Okay? So there's our 2 points that we actually plot on the x-axis. So we'd come out here 3 units.
Oh, wow.
So if you forget, those are kind of shortcuts anyway we're remembering. Go all the way back to the equation and say, okay, what works? What works in the equation? Now, there are some other points that we're going to acknowledge here, which are the ends of the, what are called the conjugate axis. This is the transverse axis, connects the two branches. The other axis is that's called the conjugate axis, and the ends of the conjugate axis are actually the b values. So in this case, if we go up 4 units, and I'm not going to call that a point because it's not a point on the hyperbola, and down 4 units on the axis that's perpendicular to the transverse axis, the conjugate axis. Does anybody remember what those are for?
It helps you draw a more accurate sketch.
Right.
Because you go up the same distance from where you plotted A. And that kind of...
Okay.
I can
It
see in
is
my
it
head.
is to graph, and we can kind of develop some asymptotes, some guides for each branch of the hyperbola.
Would that
So-
be horizontal asymptote?
No, that.
The diagonals would be asymptotes.
Oh, okay.
So this little, for lack of a better word, this little AB rectangle, the diagonals of that rectangle will serve as asymptotes for each branch of the hyperbola. So there's one asymptote. There's the other. So if we start here, open this thing up. Kind of tells us how fat or skinny each branch of the hyperbola is. So the transverse axis is on the x-axis because the x term is positive. This conjugate axis, where I came up 4 units and down 4 units because b was 4, helps us to draw some asymptotes that serve as kind of guides for each branch of the hyperbola. So the set of points that are blue comprise the actual points on the hyperbola. So if this point is on the hyperbola, sorry, I don't have the foci yet. Where are the foci? 5 units from the center on the transverse axis. So there's a focus, and there's a focus. So this point on the hyperbola, the difference of these two distances is fixed according to the definition. And in fact, in this problem, it is what is the difference of those two distances. It would be twice A, and A is 3, so twice A would be 6. This larger distance minus this smaller distance is 6. for this particular hyperbola. All right, save a little bit of time. Let's just kind of, yes, question, Jonathan.
So in the case with the hyperbola, will a squared always be under x squared?
No. Let's talk through a problem without kind of going all the way through it. So let's say the y squared term is first. Now, in my previous example, my first denominator was smaller than the second one, so let's just reverse that. Let's say this is 25. So there's our equation. So other than locating a center that's somewhere other than the origin, let's just make a rough sketch. So where is the center of this particular hyperbola?
-2, 5.
Negative 2, 5?
Positive 5.
Negative
5, negative 2, right? H is 5. K is negative 2. So 5, negative 2. So everything kind of stems from there instead of stemming from the origin. Transverse axis. Is it parallel to the y-axis or parallel to the x-axis?
Parallel to the y.
Parallel to the y, because the y squared term is first. So to get to the ends of the transverse axis, how many units in which direction?
5 units in one.
5 up and 5 down. So there's 1, 2, 3, 4, 5. There's a point on the hyperbola. 1, 2, 3, 4, 5. There's another point on the hyperbola. To get to the ends of the conjugate axis, we would go 3 units from here. Just put a little X there. It's not a point on the hyperbola. And that would be helpful for drawing the rectangle. I'm not going to draw that. The asymptotes of which serve as, or the diagonals of which serve as asymptotes. The only other point that we would need to plot would be the foci, or foci. Actually, I don't know which it is. I think I've probably heard foci more, but I've heard both. Where would the foci be? Tell me how to get to the foci from the center.
Thank you. Add the 2 together and square root 5.
What's the numerical value for C?
34 square root.
Square root of 34? So we would come from the center up here, the square root of 34 units, right?
Huh.
Beyond, it's got to be larger than A, because C is the
Large.
largest of the 3 based on the Pythagorean identity. It's got to be. And we would come from the center down the square root of 34. So roughly, the hyperbola is positioned in this fashion, right in the plane. We could do better if we drew in the diagonals, which would serve as asymptotes. Any question on hyperbola before we leave that one? Okay, that should finish us with the appendix in the back of the book. So what's important from back there? Everything that we reviewed from lines, all kinds of point slope, slope intercept, slope in general, all the linear stuff that we did. Circles, definition, equation of a circle, definition of ellipse, equation of an ellipse, definition of hyperbola, equation of the hyperbola. So all those conic sections. Let's go back to the front part of the text. We've kind of done justice, I guess, to 1.1 through 1.4, which is supposed to be prerequisite material. We didn't do much with 1.4, and we're not going to do that today. You probably already know everything there is in 1.4. If you have a graphing calculator, that's what it is, how to zoom in, what's your viewing window, how to interpret what it is that you see. You know how to do that stuff. By the way, graphing calculators are not required in this class. I bet you if we took a poll, I bet you probably more than 75% of you would have one, but it's not necessary. And in fact, sometimes on test questions, it's actually off limits, because I'd like to know if you know how to graph and not whether or not your machine knows how to graph. So let's go on past that prerequisite material. And I'm hoping some of this is prereq also. Exponential functions. But we'll kind of start with that as the so-called new material in this text. Functions that look like this. Where a is something greater than 0, but not 1. It's not very interesting if a is 1. If a is 1, we have 1 to the x. Well, 1 to the x is not very interesting, and probably really it doesn't fit into this section. If x happens to be an integer, then we kind of know what that means. We know that a to the, let's say, n, if n is an integer, that means that a is used as a factor n times. We know what that means. A cubed, a times a times a, used as a factor 3 times. So we can get a handle on that. There's some other things that are a little more difficult to get a handle on. What is a to the square root of 3? Because this is a nice continuous function. It's not discrete in the fact that we've only got it defined for integers. It works for all values.
1/3.
So what does that mean? Or what does a to the 1/2 mean? You can't say it means that it's used that many times as a factor. Somebody said what a to the 1/2 means. What is that? That's really the square root of a. So it's not necessarily always going to be clean in a sense that that's how many times that letter a is used as a factor. A to the square root of 3, well, that gets kind of tough to figure out what a to the square root of 3 is, depending on what a is, of course. But we do know that a to the square root of 3 is somewhere between a to the 1.7 and a to the 1.8. Okay? It's in there somewhere. A little more difficult to deal with, because square root of 3 is 1.732, which is somewhere between 1.7 and 1.8. Here's another one that's a little pesky to deal with. A to the 0.
1.
So we know that means 1, but there are, I think, 2 really, really good reasons why a to the 0 is 1. Can you think of those?
Because it's only 1 times itself. It's only the a. It can't times it again.
Right? So that'd be a to the first, right? If it's just a, you'd have a to the first, it'd be a, which is equal to a. So I have a used as a factor 0 times, which, by the way, that's not what it means, but it kind of sounds like that. So why would something to the 0 power, not 0 to the 0, but 2 to the 0, 8 to the 0,
Divided by 6.
You're not multiplying it by itself anytime.
okay? You're not multiplying it by itself.
So it's just
You're kind of dividing it by itself once.
Okay, I like to get the division in there. Let's see if you remember this property. How do you handle that? You subtract the exponents, right? Well, if you subtract the exponents, what do you get?
0 to the 0.
You get a to the 0, but look at the original fraction. What's the value of a cubed over a cubed?
1.
It's 1. So there's one justification for why something to the 0 power is 1. Another justification let's kind of go backward from some of our properties. A to the 0 minus n, well, that's really a to the minus n, right? Because 0 minus n is minus n, or negative n. How does that definition go? How does a negative exponent work?
Puts it in the denominator.
Puts it in the denominator. So isn't this 1 over a to the n? Is that correct?
Yeah.
Well, let's go back to this. If we have subtraction in the exponent position, isn't that the same thing as a to the 0 divided by a to the n? Is that correct?
Yes.
If you had this, you'd say
That's 1.
0 minus n, right? Which would put us back here. So I'm kind of using that property in reverse. So a to the 0 minus n is a to the 0 over a to the n. I think there's your equation that kind of validates, right? The denominators are the same. If those two fractions are the same, the numerators better be the same. So a to the 0 better be equal to 1. So there's a couple of good ways with existing properties we can justify that a to the 0 is in fact 1. How about a to the p over q? What's the root index here?
A to the p.
What root are we going to take? The q. That's kind of an interesting word. The qth root. Okay? So we're going to take the qth root of a and then do what with it?
To the p.
Raise it to the p power?
Is it the whole thing or just the a?
Okay, it could be that. We could take the root index, in this case q, the qth root of a, raise it to the p, or what else could we do?
You could do a
To the p.
1 over q.
Okay, let's hold that thought. But I heard a to the p and then do what with that?
Square or q root it.
So it doesn't matter when you raise it to the p power and when you take the q root, as long as you do both of those. So if you think about that, 16 to the 3/4. That could be
16 that we said there.
the 4th root of 16, which is 2 cubed, which is 8. Probably picked a bad value here. Or we could take 16 cubed. Might need some help from you with that. And then take the 4th root, right? So if somebody runs that through their calculator, I am really hoping that it's going to tell you that that's 8.
For the p and q
Yeah.
one, could you have written it out as a to the 1 over q to the p power?
The whole thing?
Yeah.
Yes. Now, her question is that the same as that? And it is, because what's an exponent? We're getting all the exponent properties, so we probably are just reviewing them as we go. We won't need to actually write them out. When you have a power raised to a power, what can you do with those powers? Multiply them. So if you would multiply these two, you'd be right back here. So that is a legitimate representation. And that really is this, right? That's a to the 1 over q, which would be the qth root. And then we would raise that to the p power. See if there's one that we didn't get there. Okay, the only exponent property we didn't get going through those problems would be this one. So let's just put it up here so we've hit them all. If you have a product to the x, we can take each thing in the product to the x, right? And that's the only exponential property that we didn't get. y equals 2 to the x. We're plotting points on that. Let's just get a small number of points over here. Try to plot them in a fashion where we're developing this graph from left to right. If x is negative 2, what's 2 to the negative 2?
What have? Negative.
I mean, negative 1, negative 4.
I heard a variety of answers there.
1/4.
1/4? Does that
Yeah.
sound right? 2 to the negative first,
1/2.
1/2.
2 to the 0,
1.
1. So the base doesn't really matter there, right? 3 to the 0, e to the 0, they're all 1, so they have that in common. 2 to the 1
2.
and 2 to the 2,
4.
4. So negative 2, 1/4, negative 1, 1/2, 0, 1, 1, 2, and 2, 4. So I don't think it's a mystery that 2 to the x has that kind of a shape. That's kind of what all exponential growth type functions look like. What if we had two to the negative x?
Decay.
That's going to be a decay function, and we should basically get the kind of the same values kind of interchanged here. Not function like interchange x and y, but isn't this the same thing as 1/2 to the x also? 2 to the negative x is 2 to the negative 1 to the x, right? If it's 2 to the negative 1 to the x, then it's 1/2 to the x. So either way, it's the same graph. So if we plotted some points, negative 2, well, the first thing we do is negate negative 2, which is 2 to the 2, which is 4. The negative of negative 1 is 1. The negative of 0 is 0. The negative of 1 would be 1/2, and the negative of 2 would be 1/4. So very similar values, kind of flip-flopped, right, on the other side of the y-axis. So we've got a 1/2 here, a 1/4. We've got 2 here and 4 over here. So this dotted line graph is 2 to the negative x, a decay type function. This is 2 to the x. About 1 minute. Let's see what we can put in 1 minute here. 2 to the x minus 3. How is that different from 2 to the x? Shifted
Horizontally to the right.
to the right 3 units, okay? So this is y equals 2 to the x so it's in the exponent position, so it's kind of, we subtract 3 from everything before we raise 2 to that power, so that has the net effect of shifting it to the right 3 units. Okay, this has a couple of things. So in fact, I'm going to rewrite that. Negative 3 to the x plus 4. What's the plus 4 do?
Shifted it up.
Everything goes up 4 units, right? So that shifts everything up 4. What's that negative sign do?
Reflected across the x-axis.
Okay, we just flip them down on the other side of the x-axis. So if it was up 3 units, now it's down 3 units. If it was up 5 units, now it's down 5 units. So that kind of reflects it right on the other side of the x-axis. So we'll reflect it over the x-axis. So we'll reflect it and then lift everything up 4. So, all right, so we will start tomorrow with some more specifics about the number e, and hopefully try to get back on the syllabus. I'm working hard. Be patient with me. See you tomorrow.